Hi guys, I will explain laminate theory from thin plate kinematics to summary. I have a quiz for you. What is the correct description about the plane perpendicular to the neutral plane in the classical laminate theory? Number 1. The plane keeps its whole area flat and perpendicular to the neutral plane all the way before and after deformation. Number 2. The plane cannot keep its whole area flat and perpendicular to the neutral plane after deformation. The assumptions for classical laminate theory are as follows. All the layers are perfectly bonded to each other so that no relative slip should not be allowed. Material properties of each layer are homogeneous, orthotropic, and linearly elastic. All the sections perpendicular to the midplane remain straight. Straight lines perpendicular to the midplane remain straight and normal to the midplane. The displacements are small compared with plate thickness. Thickness is small compared with the other dimensions. Transverse shear strains, gamma zx, gamma zy, and the transverse stress, sigma z, are all negligible. Classical laminate theory is applicable to thin plate, of which another name is Kirchhoff-Love plate. As explained in the previous slide, in that theory, all the xz and yz sections keep their shape flat and normal to the neutral plane before and after deformation. Also, all the lamina plates are perfect bonding each other so that no relative slip can be allowed between them. In the real deformation, those are not true, but this theory is accurate enough to most of real thin plate applications. Now let's look into the lamina theory. We have a thin plate with thickness T. A yellow color indicates the neutral plane. Assuming that thin plate deforms so that a plate A on the neutral plane moves to A prime after deformation, then the displacement of this movement are U0 along the x-axis, V0 along the y-axis, and W0 along the z-axis. Middle picture shows the detailed description related to the deformation of vertical section xz plane, including the point A prime. The slope theta x of neutral plane at point A prime is delta w over delta x, which is equal to rho w over rho x. On the other hand, half a thickness of plate in plus z-axis experiences compression, and the other does tension. Let's look into the deformation of a point with distant z perpendicularly away from midplane. A red arrow describes that deformation, which can be expressed as z multiplied by tangent theta x. For the small theta x, tangent theta x is equal to theta x. Therefore, the displacement of this point is equal to z multiplied by rho w over rho x. Therefore, displacement in x-axis is equal to u0 minus z multiplied by rho w over rho x. In the same way, the displacement in y-axis is equal to v0 minus z multiplied by rho w over rho y. We can calculate the displacements u, v, and w using the kinematics of deformation in the previous slide. Now, we can derivate the equation to calculate the strains from those known displacements. Strains can be obtained by calculation of derivative of u and v with respect to x and y for normal strain, and with cross respect to x and y for shear strain, respectively, by substituting the displacements u, v, and w here. We can get the full derivative expression here. Introducing the symbols for curvature, kappa x, kappa y, and kappa xy, we can express the equation in a simple form shown here. Now, we can calculate the stresses of the plate. We have already calculated the strains and the curvatures, and all the elements of a stiffness matrix are composed of Young's modulus and the Poisson's ratio known to us already. Forces can be calculated by integration of stresses over the thickness with the unit length. And also, moments can be calculated by integration of stresses multiplied by moment arm z over the thickness with unit length. At this time, you may have a doubt why the name of these guys have 6 in their index instead of 3. That will be clear later. All the forces on the tiny square piece of thin plate can be expressed as shown in the picture. We have 2 normal forces and 1 shear forces because nxy is equal to nyx. We have just 1 shear force. The forces per unit length acting on the xz and yz sections perpendicular to the neutral plane can be calculated by integrating the stress over the thickness. In our analysis among forces, nz, nyz, and zx are all equal to 0, and also among the stresses, sigma z, sigma yz, sigma zx are all equal to 0. Therefore, we have just 3 elements in force and 3 elements in stresses. As the same way in the forces, all the moments on the tiny square piece of thin plate can be shown as in the picture. We have 2 bending moments, mx and my, and 1 torsion moment, mxy, because myx is equal to mxy. A positive bending moments of green lattice make tension stress in the positive x-axis, which is lower than midplane. And also, it makes compression stress in the negative x-axis, which is upper than midplane. Positive torsion moments of red lattice make positive x-axis rotate to positive z-axis, and also make positive y-axis rotate to positive z-axis. The moments per unit length acting on the xz and yz sections perpendicular to neutral plane can be calculated by integrating stress multiplied by moment arm z over thickness. In our analysis, mz, myz, and mzx are all equal to 0, and also sigma z, sigma yz, and sigma zx are all equal to 0. Therefore, we have just 3 elements in moment vector, and also we have only 3 elements in stress vector. The relationship between stresses and the strains can be expressed in the matrix equation shown here. Normal stress sigma z and shear stress tau yz and tau zx are deleted because all they are zero in our analysis. On the other hand, stiffness matrix is symmetric. Consequently, corresponding Q elements can be ignored, like in this picture. Therefore, we end up with simple form with a normal stress sigma x and sigma y and the shear stress tau xy. Substituting the mid-plane strain and the curvature for epsilon x, epsilon y, and gamma xy, we can calculate the stresses. These Q matrix elements explain why these guys have 6 in the index of their names. Furthermore, because of symmetric properties, Q21 is equal to Q12, Q61 is equal to Q16, Q62 is equal to Q26. Then, how can we calculate the forces and the moments for laminate plate composed of several composite layers? Like this picture. Each layer has different quarter angles. This is the topic of next video. Answer to the quiz is, the plane keeps its whole area flat and perpendicular to the neutral plane all the way before and after deformation. Here we have a summary. Classical laminate theory is applicable to thin plate. Another name is Kirchhoff-Love plate. All the X, Z, and YZ sections keep their shape flat and normal to the neutral plane before and after deformation. No relative slip can be allowed between layers. All the strains of any one point of plate can be expressed in terms of strains and curvatures of neutral plane and Z coordinate perpendicular to neutral plane. All the strains necessary for classical laminate theory are 2 normal strains and 1 shear strain, by which 3 degree of freedom forces and 3 degree of freedom moments can be calculated. If you watch the previous videos, you can easily understand upcoming videos. In the previous video, E0033, I explained the price tier due to in-plane deformation and the stiffness coupling. Recently, I explained the price tier due to out-of-plane deformation of corded belt at angle. The next video is price tier part 7. I will explain the laminate theory part 2. Please hit the like and catch the brand new videos by pre-subscription. So what are you waiting for? See you at the next video. Goodbye guys.